So for our final talk before our workshop session, I'm going to give a talk based on some work that I did with my colleague Dave about priority ordering and MEV taxes. So what this talk is going to be is partly about the mechanism idea of MEV taxes. And this is this idea that we're excited about because it's a way for applications to capture MEV for their own users. It works on a composable general purpose blockchain without any need for extra infrastructure. And it works even out of the box on chains like the OP stack if those chains follow a certain set of rules that we call competitive priority ordering. But there is a catch to those, which I'll be talking about in depth. So we're excited about MEV taxes as an idea, but I also want to make an argument, which is I think there's a philosophy of how we should be constructing blocks. It's necessary for enabling MEV taxes, but it's important for a lot of other things. And I think it goes to how we think about blockchains themselves. And that's that I think blocks, the way that we order transactions in a block should be by priority fee paid by those transactions. I think this enables MEV taxes, I'll talk about. And it works. It's really easy to build. Already, a lot of blockchains are Ethereum-based blockchains are built to be able to support it. But it does have a catch, which is that enforcing it trustlessly is an open problem. And I think this is part of the reason I'm making this argument is I want to try to encourage and incentivize research that is trying to solve the pieces of this problem, which we'll talk about. I also think it matters a lot for the L1 and L2 roadmap. And I've seen a lot of ideas thrown around in where people think the L1 or L2 roadmap should go that makes me nervous, in part because I think it potentially makes these kinds of solutions impossible, but also because it violates, I think, some of the philosophies that motivated us in developing the protocol. So I want to try to see if we can make some of you nervous about these ideas as well. So when I talk about priority ordering, I think it goes to a relatively deep question about how we think about blockchains. But it starts with this narrow question of how do we order transactions once we have them in a block? And there are three dominant paradigms for how this currently is done. And I'm sort of representing them here by three blockchains that roughly use these approaches. So one is called proposer-builder separation, which is what Ethereum L1 primarily uses. One is called first in, first out, or first come, first served. That's what the Arbitrum 1 L2 uses. And another is priority ordering. And that's how OP stack chains by default operate. And I think this kind of goes to how we think about the blockchains themselves. And I think all these philosophies are present in all these chains, but they're emphasized into different amounts. I think with Ethereum, people are primarily thinking about it, and one reason that PBS has developed, in terms of it's an incentive engine. People are very worried about Ethereum being incentive compatible for block proposers. And so that's what drives them toward proposer-builder separation, which is a way to make things work in the incentives of the proposer, to try to incentivize the proposer to build blocks correctly. Another model vision for how blockchains work is the one emphasized by Arbitrum, which is a blockchain as a time-stamping service. The idea is this transaction is happening at some time, and the point of the blockchain is just to record what time it happens, and then we're going to sort out what the execution means after that. And the third, and the one that's represented by priority ordering and what the OP stack implements, is a blockchain as a fair auction platform. We're trying to run an auction here, and we have auction infrastructure, and we want to make that auction work as fairly as possible for the participants. And I think these approaches mean that there are three different ways to try to solve MEV. One that's been the approach that we've tried to take with Ethereum is through alignment, trying to make it in the incentive of the block proposer to reduce the MEV. So building applications in a way where block proposers, best that they can do is to allow transactions to go through and extract less MEV from these applications. This is a very hard problem because in this case, the user is directly on the other side of the proposer, often in a zero-sum or negative-sum game. But this is what I think a lot of the attempts that we can do without making protocol layer changes have involved. Another is by trying to mitigate MEV by reducing the latency. As CMAC talked about, just reducing the block time actually reduces lever and other kinds of MEV in a lot of cases. And so just reducing latency really fast means that you get rid of a lot of kinds of MEV, although you can't really reduce it to zero. And the third way to try to do it is through auctions, trying to auction off the right to interact with a smart contract in order to capture that value for the contract or the application. And that's the one that I'm going to talk about today. So for some quick review on MEV, and the kind of MEV that we'll be talking about here, we're talking about competitive MEV. When there's something available in a smart contract and the first person who goes to grab it is able to get that money. So this is how AMM arbitrage works, the kind of MEV that leads to loss versus rebalancing, which CMAC talked about. This is how filling an open Uniswap X order often works. It's how buying from a Dutch auction that's going on chain works. Sometimes there's some value that you can get just by being the first person to interact with a smart contract on chain. And in most cases, all of this MEV by default goes to the block proposer. And that's because searchers, people who are trying to fill it, are competing with each other to fill this, and ultimately are paying the block proposer to get included first. And one way this naturally happens on some chains is through priority fees. So each transaction sets its own priority fee. If a sequencer just simply sorts the transactions in descending order priority fee, then typically whichever searcher sets the highest priority fee is going to be the one included first. So they're going to pay most of their MEV to the proposer. And this is a kind of on-chain auction where all of the value goes to the block proposer. But the contract would rather have this MEV for itself rather than giving it to the block proposer. So how can we implement that? The idea of MEV taxes is that a smart contract can actually look at that priority fee. They can look at what the transaction is paying to the block proposer, and they can charge a fee proportional to that. So what if we just charge a really huge fee relative to the priority fee, say 99 times the priority fee? Well, what actually happens is that means that 99% of the MEV that would otherwise have gone to the proposer ends up going to the smart contract. And to understand a little bit how this works, because it's not intuitive. Oh, is this not a? Sorry. Yeah, there we go. To understand a bit how this works, because it's not entirely intuitive, the idea is in the previous way that MEV works, when you're not using MEV taxes, typically the searcher is going to make some profit that's represented in green on this diagram, and then they're willing to make some other payment to get included. And that payment comes from the MEV, but ultimately, that's not going to go to the searcher. That's going to go to the proposer. Because if they set it any lower, if they paid any less, then some other searcher is going to get that opportunity because they're going to pay more to the proposer. And so in the previous state, without MEV taxes, all of this payment is going to end up going to the proposer. It goes into the priority fee. After MEV taxes, if you're charging a fee that is proportional to the priority fee and is much larger, what it means is the searcher is going to still make the same profit and make the same payment, but who they pay is going to change. They're going to have to reduce their priority fee by a significant amount. But that's OK because every other searcher is in the same situation and also has to reduce their priority fee. So the transactions are still going to be ordered in the same order. But then they're going to have to pay a much larger MEV tax to the application. And so ultimately, most of that MEV is going to end up going to the application. And you can imagine charging a much larger multiple than 99. So you can ultimately, in practice, get the vast majority of the MEV that would otherwise go to the proposer. So there's a lot of cool use cases for this. We've talked a lot about AMMs that capture MEV, and this is one way to do that would be to charge for the first transaction in a block that interacts with an AMM. But you can imagine lots of other ones. We talk about some of them in the post, including Dutch auctions that reduce the loss versus fair that they'd otherwise be subject to. Order routers like Uniswap X, where searchers are optimally routing users to the best route, and they're competing with each other to give the best price to the user. And the idea is if we charge a fee that is a fee that is to the searcher that is proportional to the to where the transaction gets included, then whoever gives the user the best price is guaranteed to be included top of the block. There's other ideas like having an oracle that can capture value created any value created by their updates, and even you could imagine adding this into a wallet in a way where any backrunning MEV that a transaction a user's operation creates could be captured by that user themselves. So I think this design has a lot of benefits. One is that it's really simple. On the smart contract itself, it's just a couple extra lines of Solidity. It doesn't require any changes to the sequencer typically, or at least like OP stack sequencers, because it's the actual default transaction ordering in Geth and Reth. And it doesn't require the application to build any additional off-chain infrastructure. So it's a lot simpler for an application just to plug in and add MEV taxes to what they're doing. The other benefit is that it keeps the application maximally composable and atomic with other on-chain actions and other on-chain liquidity. So in an off-chain auction, like the one that Uniswap X uses today, when somebody bids to fill an order, they can't necessarily say, I only want to win this order. I only want to place this bid if I can get a particular transaction included on chain, if I can fill it on some particular path on chain. And that means that you may, even if you can see an opportunity to fill an order on chain, you may actually not bid for it because you have some risk that your order could be, you could win an auction, but then actually end up losing the separate auction on chain to get your transaction included. Whereas with this auction, you can actually make your bid effectively conditioned on your transaction completing by trying to fill it in an on-chain transaction. If your transaction reverts, your bid is effectively canceled. And so it's really only the highest bidding successful transaction that will end up executing the user's order. And this is particularly useful for a complex auction like Uniswap X, which is intended to support routing of an order by off-chain fillers and searchers to on-chain liquidity. And for that to really work, you want it to be atomic with other on-chain liquidity. But there are a lot of challenges that come with MEV taxes. And one of the biggest ones is that it requires, it's not incentive compatible for the block proposer. For MEV taxes to work, the block proposer has to promise that they're going to obey these rules of competitive priority ordering. One of the most important of which, as Max talked about a lot, is not censoring transactions. Because if you can censor other transactions from other bidders, other searchers, then you can potentially win with a lower priority tax and pay a lower MEV tax than you should. So for this reason, it's not currently possible on L1, which is dominated by the MEV boost auction, which requires paying the maximum amount to the proposer, and therefore any builder who tries to follow these rules is going to tend to be outcompeted by ones that don't. And enforcing this trustlessly is an open problem, but I think we have some there's some line of sight on potentially solving it, including some of the ideas Max was talking about earlier. Another issue is that this is an on-chain auction, which means that failed bids are going to result in reverted transactions. Everyone who tries to fill a Uniswap X order, for example, after it's already been filled, that's going to result in them paying some gas because they have a reverted transaction included on chain. There may be ways to prevent this by having the sequencer, for example, selectively not include transactions if it can be proven statically, verified statically, that it's going to fail because, for example, it tries to fill a Uniswap X order that was already filled. So I think there's a lot of interesting research to be done there as well. I think a minor issue is that any application that charges a MEV tax is going to tend to have a much lower priority fee than any other transaction because it's charging a very high multiple on that priority fee. And so if blocks are full, which means that priority fee has to be higher than 0 to get included in a block, generally any application with a MEV tax is probably going to be priced out. That's not very common today, particularly on L2s that use EIP 5059. So like Base, for example, 99.7% of blocks would be able to fit an additional million gas of transactions in them. So I think it's not a major issue, but it is one potential downside. And then finally, as Karthik talked about a little before, when you have multi-app MEV, MEV that requires interacting with 2 applications at the same time, attributing the MEV between those applications is a complicated problem, and the way to design MEV tax, I think it's outside the scope of this talk, but designing the MEV tax of an application in order to capture more MEV from multi-app interactions is a complex problem that, again, I think deserves a lot of study. So that's the MEV tax mechanism. But like I said, it requires this priority ordering primitive, and I think that means we should think about why should we be ordering transactions this way? And my argument is I think we should. I think it's a very powerful primitive for a platform to offer. And the reason is allowing applications to see the priority of a transaction and know that it's actually the highest priority of a transaction that was willing to interact with that allows every application on chain to basically run its own MEV capturing auction. Any application that is using this chain gets to take advantage of the massive amount of work that's gone into actually guaranteeing this auction on the protocol layer. I think that's a really useful thing for a blockchain to provide. I really liked Max's or Vitalik's terminology about eating the complexity at the protocol layer, at the platform layer. Let's solve this very difficult but kind of definable problem of having the rules of competitive priority ordering. And then everyone can just take advantage of this actual research breakthrough and engineering lift and build applications on top of it that take advantage of that. So some of these problems that need to be solved, I think Max mentioned the most important one, which is censorship resistance. And I think there's a lot of ideas on how to implement that. I think multiple concurrent proposers and inclusion lists are some of the families of them. But generally what's important here is that it has to be fast censorship resistance. It has to be same block censorship resistance, or at least potentially very close to same block censorship resistance. Otherwise, it's not going to be MEV useful. It's not going to be MEV relevant. Another is pre-transaction privacy. I think there's a lot of ideas on how to potentially address that using cryptography or trusted execution environments. And final one is no timing advantages, having nobody be able to act later than other participants, so that they get sort of basically a last look on any competition in that chain, which could lead to adverse selection or winner's curse for other participants. And so I think Braid might be an approach to that. Dave and I have a paper, an idea called leaderless auctions, which is kind of trying to throw ourselves at that particular problem. I'd say that's probably the thorniest problem, but nevertheless, it's still all these problems are kind of finite definable things. We can sort of talk about them. The general problem of solving MEV is such a hairball when we try to even think about what that could possibly mean. Whereas designing a platform that guarantees these, okay, we can sit down and get to work on it. And I think that's really appealing to me, is let's try to solve these problems at the protocol layer once if we can. So what are the alternatives for how we order transactions? One is what Ethereum L1 primarily does today, which is MEV Boost, which is an ex post auction for capturing MEV entirely for the proposer. And I think this is it's incentive compatible and it's effective, but it does have significant deadweight loss. There's because and CMAC talked a little about this. Just maximally capturing MEV is not necessarily to the benefit of there's efficiency losses. If you're capturing MEV, it's not just a distributional problem where the chain is making more money and the users are losing more. It's actually potentially reduces just value reducing, and so it seems like just a bad way to actually for the chain to actually charge fees. It would be better for them to charge just a higher transaction fee potentially, but not actually capture MEV. Another approach that some like Arbitrum have pushed more for is first come first served. This, as CMAC talked about, it's an imperfect solution to MEV because even some kinds of MEV you will still have even if transactions are block time is infinitesimal and you have first come first served. For example, if there are jumps in price, you still get some loss versus rebalancing there, and it's even more difficult to decentralize. And then the final category is decentralized builders, of which like Flashbots is Suave is an example. I see this as basically a superset of priority ordering and MEV taxes. Priority ordering and MEV taxes is a very simple auction, but there are other ideas for auctions that you could implement. And I think Suave is a platform for trying to implement more complex auctions that could give you things like bid privacy or sort of more complex ordering rules. And I think that's and potentially some additional efficiency that you might lose from priority ordering. So I think it's a really interesting area to look at. But I see priority ordering as kind of the MVP of how to run a fair auction on chain. So like I said, with this priority ordering idea in mind, I get nervous about a lot of the things that people talk about in the L2 and L1 roadmaps. And that's kind of the natural state of an Ethereum researcher is nervousness. But I want to try to explain why I feel this and maybe instill some of it in all of you. And so some things I think that make me nervous about what people think about L2s. One is to normalize the idea that sequencers should be extracting maximum value from blocks, either by selling off the right to extract MEV from them ahead of time in an ex-ante auction, or from auctioning off the MEV ex post, the way that MEV Boost does. First, I think this is, like I said before and CMAC said, it's just there is deadweight loss in charging fees this way. It is, I think, in most cases, better to just charge a fee to the users, charge people to use the chain, than it is to collect revenue by extracting MEV from users. Because in general, people may just not be able to use certain kinds of applications. You may not be able to design or operate certain kinds of applications if you know that the sequencer is going to extract MEV. Whereas if actually they're not able to or they commit not to, then you could do those. And so that's deadweight loss for the system. I also think while we have centralized L2 sequencers, I think we want to decentralize them, and it's really important to decentralize them. But while we have them, we should use them and not screw over users. And I think, in fact, arguably, this is the right way to decentralize them is to provide these strict rules about things like priority ordering, and then we can allow anyone to run the sequencer, and as long as they're constrained in this way, they won't actually be able to extract excess MEV from it, right? And so I see this as the path toward sequencer decentralization. But I think if we start with having sequencers doing kind of really offbeat things, I think we're sort of just giving up a lot of the advantages we already have today in the way the system works. The other approach that people talk about in L2s, and again, like I said, Arbitrum leans toward this philosophy, is first come, first served ordering. First come, first served is hard to, I think, even define what it would mean in a decentralized context. and I think certainly difficult to enforce in a decentralized context. Although again, I think there's some interesting work on the idea of how we might do this with with end parties, with like fair ordering protocols like Themis being one example. Fair ordering, by the way, I think is an I don't know about oxymoron, but it's just not what we would call this in any other context. When people talk about like HFT and they say it's really unfair that whoever trades first and you have like a 5 nanosecond advantage is able to be the first person to trade, they call that unfair. So first come, first served in the traditional financial context is unfair ordering. So I think it's a weird, and I talked to some of the people who coined it, and they're like, oh yeah, we agree with that. So I don't know why people keep using fair ordering. But we could say first come, first served, or first in, first out. Got a lot of terms for this, but I think it's difficult to decentralize, and it doesn't eliminate all kinds of MEV. There's a lot of stuff you can do with an auction that you can't do with just a first come, first served system. And you can capture a little more of the MEV. Again, potentially some from things like jumps in price. So that's the L2 roadmap. What makes me nervous on the L1 roadmap? Like everything. But some examples, I think, of some of the themes that worry me. So one is pre-confirmations or basic pre-confirmations. This idea that proposers should be able to say ahead of time what given confirmations that transactions will either be included or succeed. And again, like there's a lot of different designs for this, but in general, I think introducing this idea that someone can actually they can violate the rules of priority ordering, that we can have someone get included just because they submit a transaction first, rather than because they're bidding a higher priority in this auction. That's much more subject to manipulation potentially by the proposer, and generally it compromises the ability to do an auction like this. Another example is enshrined PBS. Enshrined PBS you could sort of think of as making it mandatory to extract maximum MEV from every block. And first I'd say, like, just in general, of all things, like, why would you want to guarantee that? Like, sort of, we have this moment of grace where maybe sometimes proposers don't extract maximum MEV, and we're going to say in the protocol it is actually, enforced that you must sandwich every user to the maximum extent of your ability. So, like, I think that's sort of just a weird way to think about this. But it also makes priority ordering and MEV taxes impossible, so it's another downside of it. Execution tickets and execution auctions, anything that's doing an ex ante auction for the right to extract MEV. In addition to the general problems of proposers capturing MEV, the deadweight loss and the distributional effects, it also sacrifices attributability. It's much harder when you're selling off the right to sequence and to build an entire block or to sequence an entire chain. How would you, even if you wanted to, how would you distribute the revenue from that to applications on the chain? It's effectively impossible in the general case because someone might be paying, for example, for the right to interact with an application that then doesn't actually, the option value to interact with it, that they then don't actually execute. So, maybe someone should be paid even if you didn't trade against them, even if you didn't access their application on that block. But there's really no way to know about that in a general purpose blockchain. There's no way to model this. So, it makes it basically impossible to try to even distribute this through to the applications or to the users who it came from. And the final thing that makes me nervous is I think there's been a lot of interesting work done from the Ethereum Foundation and Ethereum researchers around inclusion lists. And I think it's going in like roughly the right direction. But there's a strong philosophical orientation of people working on inclusion lists to basically nerf them. To say we don't want there to be any MEV in these inclusion lists. Because if there's any MEV, then maybe there'll be an incentive to build centralized infrastructure around it, and that's going to compromise the ability to do censorship-resistant things on it. And I just think one of the biggest benefits that you get from censorship resistance is the ability to have MEV-relevant transactions in those inclusion lists. And so if you sacrifice that, you're just losing a lot of the benefit. And you also, I think it weakens the argument for it. And this is kind of a real politic point, but like if you're arguing for an inclusion list entirely on the basis of like OFAC transactions, I think that's not the great like policy argument. If you're arguing for it on the basis of this is better for users because it actually allows us to build MEV-resistant applications, that is to me a much more convincing argument and like basically a better argument for it. And it's more in line, in my view, with the actual purpose of blockchains, is we want this to actually be a fair system. We want everyone to have access to this. And so. Yeah, so I think trying to build inclusion lists in this way is really giving up on solving this difficult problem of building it in a way that's collusion resistant and MEV resistant, and taking this like cheap way out, but really sacrificing a lot of the benefit for it, and I think some of the policy argument that it could otherwise give you. So in my view, we should have an inclusion list solution that can support MEV relevant transactions. So I'm not really I think. Much of a heretic on most of the Ethereum roadmap. I think in general, like there's some stuff we should really absolutely do anyway. One is, I think, shorter slot times, and this is, I think, gotten a lot more consensus lately. But even if I'm not in favor of first come first served on transaction by transaction basis, you have to have some block time, and it would be nice if that block time was shorter. I think that's just generally true. It's better for users. I think it is better for Mev. It sort of leans a little less on things like running this auction potentially fairly, and so to the extent we can, I think we should push for it. And I think everyone is starting to agree on that. I do think inclusion lists have gone in the right direction, particularly having inclusion lists that are enforced and presented not by the proposer of the block, but by testers or by some kind of committee. And I put like roughly, I think multiple concurrent block proposers is kind of, when you think about it that way, like a flavor of inclusion list, although one where I think it emphasizes a little more the MEV relevance, which I think is a good part of that framing. And then finally, I do think there's still going to be a place and a necessity for applications to do what they can to mitigate MEV. And MEV tax is one idea for doing so, but it certainly is not a comprehensive one, and so there's a lot of other ways for applications to be designed that mitigate MEV or that take advantage of different parts of MEV in order to provide different functionalities to users, like batch auctions and common clearing prices, which I think is really valuable. So there's still quite a lot to be done at the application layer, even as I think we should be trying to take this head on at the protocol layer. Great, thank you everyone. Questions? Ludwig.
So I have two quick questions. The first is, does this not incentivize spam under the assumptions that there's no mempool, and obviously we're using priority fee ordering for the blocks. So from the data we collected on Ethereum, the biggest form of MEV in terms of revenue is actually atomic arbitrage. And although data definitely has some problems there, it's very significant in terms of bundle count and value. And here, the transaction that is actually creating that atomic arbitrage opportunity will not have a high priority fee. So then you're incentivized to spam the chain to get the transaction right after it. But the priority fee that you're paying to be right after within that same block is not higher. So you don't have an ability to then capture that value and distribute it back to that person that got background.
Yeah, I think that's a great question. I think there are ways to capture that value. Well, first I'll say atomic arbitrage, the existence of atomic arbitrage is kind of a skill issue on-chain, in that if an order is properly routed on-chain, then there should not be a way to make money just by being the first person to go after it. And there may be exceptions to this, but in general, the reason atomic arbitrage shows up that it's profitable for someone to go in and spend the gas to actually do, and potentially pay 2 extra spreads while they're doing this, right, to arb this thing back to the right price, is because the previous trade happened at a bad price. And so the ideal thing to happen probably would be that trade is actually routed optimally or given a better price, right? So there's 2 ways for that to happen using MEV taxes. One is through the sort of DEX-specific mechanism of Uniswap X, which is Uniswap X is basically a smart order router where searchers are competing to fill the order at the best price. If we use MEV taxes for this, then when somebody puts in an order, and if this mechanism works properly, whoever's going to fill that user at the best price is going to actually be the first transaction in the block. They're probably going to be routing it somewhat optimally or filling it off of off-chain liquidity. And so that transaction should not result in on-chain atomic arb. I wouldn't really expect it to. The other possibility is if someone has just a transaction, right, and maybe it's a bad transaction, maybe it's sort of or an operation they want to do on chain, it's something arbitrary. If that does produce backrunning MEV and they're worried about that, there is a way to use MEV taxes for them to capture that. And we talk about it a little in the post, but the idea here is they can sign their intent to do that particular transaction, or the particular operation, I think is what people call it, and then they can release that to the world, and anyone who wants to submit it on chain can create a transaction that submits it on chain, and then they pay a MEV tax to the user. So if that transaction turns out to create a bunch of backrunning MEV, whoever includes it, whoever wins in actually including it and backrunning it, is going to have to pay a lot to the user for actually the right to backrun them. So this works roughly the same way as Flashbots' MEV share or MEV blocker do, but it does it entirely using this on-chain priority auction. I think these are not perfect mechanisms. One that I didn't really talk about here is all of these ideas for using MEV taxes generally involve creating a competitive auction to fill your transaction or to do something for you. That means you have to reveal your intent to the world. You may not always want to reveal your intent to the world, but I think for MEV taxes to work, you have to. So I think that's a case where things like Suave, I think, are able to do types of auctions, with sealed bids, more complex things that you can't do with MEV taxes.
The second quick question is, given that there's no very immediate path towards solving this for decentralized sequencers. Is this not incentivizing application builders to rely on a system that currently only clearly works within a centralized sequencer paradigm, which could result in two things if we don't actually solve this? A, obviously most of these apps are reliant on this centralization. The L2 itself has no incentive to then switch to a decentralized model because it would break their entire application stack. And then B, we're creating applications that are not being incentivized to design themselves for that decentralized context.
So I do think when we're designing applications to rely on priority ordering, we should do so defensively and not put a really extreme amount of trust in the mechanism. But when you think about it, what's the worst case of a proposer violating the rules of priority ordering? It's basically what happens today, which is they capture the MEV, right, instead of the application does, right? So we would end up, if you design your application right, so you're not, again, putting way too much weight on this mechanism, you can design your application in a way where you just get back where we started if the application, if the sequencer decides to start cheating you, right? And then they end up, but they're capturing the MEV right now. So I think that's not as big a worry. As for whether it leads to decentralization, again, my view is, I think this research has to happen anyway, in part because I think we should do this for the L1. I think we should try to, and I think Braid is one idea of how we could possibly do this, and try to enforce these things on Ethereum. So this research is going to happen. We're going to figure out how to make this this kind of thing decentralized. And then, yeah, again, I think the question is can we actually can we decentralize this? Again, right now, it's really hard to decentralize a sequencer because you're going to end up with all the MEV extracted, right? So that's already a really hard problem today. And I think here, this is a way to decentralize a sequencer. By enforcing these rules, that doesn't become a MEV free-for-all. That's the hope. Because otherwise, right now, I'm not sure how you would decentralize a sequencer without just giving the MEV away to everyone.
Is it does it actually provide a path towards? Because
well, here we got to have a platform that guarantees these three things, and then if it guarantees those things, then anyone can be the sequencer and it's fine. That's the basic idea. Whereas with today, what would you actually say if we want to decentralize a sequencer? What are we going to have? If we have a proposer rotation, they're going to extract all the MEV. So that's worse, right? Just among random proposers. So you're going to need some answer to that. First come first served, really really hard to enforce in a decentralized way. So I think this is roughly the only way to decentralize a sequencer, or short of trying to do first come first served, or just giving the MEV away. Benedict.
Yeah, so this mechanism is pretty dependent on the fee scheme that you use. Do you prefer a mechanism where you pay a priority fee based on how much execution you actually do, or one where you do a reservation up front, similar to Solana? Which one is more robust?
Yeah, it's a good question. And how we think about it, I think it doesn't really matter how the chain charges the priority fee, because that's going to be some really negligible number. What matters is just how the application computes it, and you could choose it to do it either way. You can't really do it based on the actual, you don't know how much gas is going to be used yet. I think the main way to do it would probably be to do it based on the specified priority fee per unit of gas, and just calculate based on that. In practice, this whole 99% thing is kind of, it doesn't have to be 99%, it has to be some really, really large number. And you don't care about having, do I have 99% or 99.1% or whatever. It's you're going to get 99.99% of the MEV. You don't really care about exactly.
And you don't really care about the reverts because the reverts don't trigger a MEV tax.
Oh, with revert, yeah. With reverts, well, I think reverts are a big deal because you're going to end up paying some base fee. And you're going to use up block space. So I think that's one of the biggest issues with these. And again, I think it's interesting to look at, could we try to at least reduce the revert problem without breaking the scheme? You want to pass him there?
It's a clarification question. So for MEV text work effectively, you need a priority ordering in terms of priority fee on the protocol layer, right? And then I had a question about the auction for the MEV text specifically. Is this auction application specific, or is it for the whole protocol?
So the idea is the protocol does one auction. It's the transaction inclusion and ordering auction, where it just takes all transactions, it sorts them by priority and by priority fee, and then just puts them in that order. That's the priority auction. Every individual application can basically piggyback on this auction, where they just look at their number. This is my number that someone bid for priority, and then they know that this is going to be the highest number that somebody bid to interact with that specific application. So each application basically gets its own little corner of the. If it wants, it can ignore every other application, just know that those numbers can be ordered uniquely for it.
Okay, and for an uninformed user, right? Because if you think of MEV as informed flow versus uninformed flow, does the uninformed user necessarily have to pay that MEV tax, or can he just pay?
Yeah. The general idea would be that normal users are not interacting with these contracts directly. They're not paying MEV taxes themselves. Or if they do interact with one, like an AMM, it's like they're actually paying no MEV tax because they're not at the top of the block. The general idea would be this is something for sophisticated searchers and fillers to actually be, they're the ones setting priority fee. I mean, like wallets are not going to do this for you.
Okay, fair. Thank you.
I have one more question. Yeah.
I think like naively there's a trade-off in the naive implementation. There's a trade-off between censorship resistance and this kind of deadweight loss via reverts, right? Where ideally we could have it so that I mean you need censorship resistance for the maximally competitive MEV tax auction on an app-by-app basis, but you ideally want to have the winner and then prune off all the reverts, right?
Yeah.
For that censoring. But I feel like there is some sort of zero cost mechanism where you could like maybe produce, I don't know, snark of some sort and say like these were included and would have reverted.
Yeah. I
Have
think
you
the
thought
ideal
about this,
censorship
and is
resistance
it
mechanism,
possible? Yeah.
that's right, would be we're not going to include, we are going to include every transaction unless it would have reverted, then we might not at least include it. I think that would be like the guarantee you'd actually want. It's probably harder to implement. And yeah, like in terms of trying to actually, and we don't get into details of how exactly we'd implement any of these solutions here, but I agree like it's probably harder to sort of prove that. But like it's at least in theory possible, given you have like it's something like Braid, you have a whole set of transactions. You could say like we're only actually going to run the ones that we know would work. It's not going to work for everything. Because just in general, like maybe it's like literally solving the halting problem to figure out whether every arbitrary transaction will revert without actually doing the work to execute it. But I think in a lot of cases you might be able to more efficiently verify that. And like one example again is if you have like something like Uniswap X, every transaction that tries to fill that after the one that successfully does is sort of knowable that it was trying to do that, and like that it's going to fail. And so you should actually just be able to maybe have them like opt in to being dropped out.